Let's see how to check whether the given vectors span the entire vector space or not. Take one example. Check whether vectors 1, 2, 0, minus 1, 1, 2, 3, 0, minus 4 of R cube span the whole space R cube. So the given vectors spans the entire space R cube if any vector of R cube can be written as the linear combination of the given vectors. Let me name the given vectors as v1, v2 and v3. If you take any vector as a, b, c of R cube, then if these vectors span the whole space R cube, then that vector should be written as the linear combination of v1, v2, v3. That is x into v1 plus y into v2 plus z into v3. If we could get the values for x, y and z, then we can say that these three vectors span the whole space R cube. Spanning the whole space R cube means the linear combination of these three vectors will go to each and every point of R cube. If it doesn't span the whole space R cube, then it will not go to each and every point of R cube. It will go to a small sub-region of R cube, that is nothing but subspace of R cube. So now after substituting all the values here, a, b, c equal to x into the first vector 1, 2, 0 plus y into minus 1, 1, 2 plus z into 3, 0, minus 4. So when you add all these, we'll get x minus y plus 3z. Then 2x plus y and 0. Then 0 plus 2y minus 4z. So now this is non-homogeneous system of equations. Now to solve non-homogeneous system of equations, we have to frame the augmented matrix first. The augmented matrix is nothing but the matrix of constants and the matrix of coefficients together written in one single matrix, that is called as augmented matrix. If you want to know more about non-homogeneous system of equations, I had previously made a video on solving non-homogeneous system. I had shared the link in the description box. Please watch that video. Now let's frame the augmented matrix A colon B as coefficients of the first equation 1, minus 1, 3 and A. Coefficients of second equation 2, 1 and note z term 0 and B. Third equation 0, 2, minus 4 and C. Now we have to reduce the given matrix to the echelon form to find out the consistency of the system. So now the first non-zero entry of first row is 1. The elements below the first non-zero entry should be 0 to say it is in the echelon form. Now first element below the first non-zero entry of first row is not 0, but the second entry is 0. No need to make this entry 0. It is already 0. Now to make the second row first entry 0, I have to apply the elementary operation. R2 changes to R2 minus 2 into R1. So no change in the first row, write it as it is. No change in the third row, write it as it is. Now second row changes as R2 minus 2 into R1. So first element of R2, 2 minus 2 into 1. So 2 minus 2 is 0. Next, R2 1 minus 2 into minus 1, corresponding element of R1, that is 1 plus 2, 3. Next 0 minus 2 into 3, 3 2s are minus 6 here. Next B minus 2 into A, B minus 2A. Now again this is the first non-zero entry of second row. Element below the first non-zero entry should be made 0. So that is done using the elementary operation. R3 changes to R3 minus 2 by 3 into R2 because 2 minus 2 becomes 0. There is no 2 here. So we are multiplying the second row by 2 by 3. So that 3 cancels. 2 minus 2 becomes 0. So the operations will be applied 0 minus 0, 0 only. No change in the first row, no change in the second row. Now 2 minus 2 by 3 into 3. 3 cancels. 2 minus 2 is 0. Next, minus 4 minus 2 by 3 into corresponding entry minus 6. 3 ones are 3 2s are minus 4 plus 4, that is also 0. Last entry it becomes C minus, I'll write here, C minus 2 by 3 into B minus 2A. After simplification, 3C minus 2B plus 4A divided by 3. This is the value. Now you have to find out what is the rank of augmented matrix and rank of the matrix A. If both are equal, then only the system is consistent, means it has a solution. Otherwise, the system becomes inconsistent. Now, rank of A is equal to rank of A is this is A. First three columns is A. So, rank of A is number of non-zero rows you have to count. There are two non-zero rows is equal to 2. Now, rank of augmented matrix we cannot say directly now because it depends on the values of A, B, C. If this term equal to 0, then the rank of augmented matrix becomes equal to 2. If this term not equal to 0, then the rank of augmented matrix becomes equal to 3. Therefore, both the ranks are not equal because it depends on the values of A, B, C. Therefore, what is this A, B, C? It is any vector of R cube. So, therefore, any vector of R cube cannot be written as a linear combination of V1, V2, V3. That is because if that is the case, if it could be written as a linear combination of V1, V2, V3, then we should get here also this term also directly equal to 0. That's not happening as it is depending on the values of A, B, C. Therefore, rank depends on the coordinates of the given vector. Hence, every vector need not be a linear combination of V1, V2, V3. Span of these V1, V2, V3 not equal to the entire space R cube. Hence, it is a subspace of R cube. Therefore, these three vectors won't span the whole space R cube. This is the method to check are they spanning the whole space R cube or not. Similarly, take one more example. Show that these three vectors span the whole space R cube. Same method, take any vector A, B, C of R cube. Then if this set spans the whole space R cube, every vector should be written as a linear combination of these three vectors. Now let's find out the values of x, y, z. So first frame the equations as before. X plus y plus z equal to a. First coordinate, second coordinates you add. So you will get x plus 2y plus 5z equal to b. Then third coordinates x plus 3y plus 8z equal to c. Form the augmented matrix. First equation coefficients 1, 1, 1a, 1, 2, 5b, second row, 1, 3, 8c, third row. Now you have to reduce it to the row echelon form here. When you reduce it to the row echelon form, what you get is R2 changes to R2 minus R1 and R3 changes to R3 minus R1. So this is because this is the first non-zero entry of the first row. Elements below the pivot must be equal to 0. If it should be in the row echelon form means elements below the pivot must be 0. So how to make them 0? By applying these two operations, elementary operation. No change in the first row. Second row changes as 1 minus 1, 0, 2 minus 1 is 1, 5 minus 1 is 4, b minus a. Similarly, third and first, 1 minus 1, 0, 3 minus 1, 2, 8 minus 1, 7, c minus a. Now, come to the second row. This is the first non-zero entry of second row. Element below the pivot must be 0. So, it is not 0 now. How to make it 0? R3 changes to R3 minus 2 into R2. No change in the first row as it is, no change in the second row, but third row changes as 0 minus 0, 0, 2 minus 2, 0, because R3 minus 2 into R2, 7 minus 2 into 4, 4 to the 8, so minus 1, then C minus A minus 2 into B minus A. So that gives you C minus A minus 2B plus 2A plus 2a. So that together c minus 2b plus a. So this gives you c minus 2b plus a. Okay. Now you have to find out the rank of augmented matrix and rank of the matrix A. Rank of A is equal to the first three columns, number of non-zero columns, that is equal to 3 non-zero rows here. So rank of A equal to 3. Rank of the augmented matrix, number of non-zero rows, again you have to count, that is also equal to 3, because whatever may be the values of A, B, C, that doesn't affect the rank of the augmented matrix A column B, because there is a pivot in the third column. So there is a pivot here, there is a pivot here, here also there is one pivot. Hence what happens, rank of the whatever may be the value here, 0, it might be any other value, doesn't matter, rank of augmented matrix remains equal to 3. Now both the ranks are equal. So rank is not depending on the values of A, B, C. Hence, what happens if the ranks are equal, the system is consistent, there exists a solution, means we can get the value of x, y, z. If there is a value for x, y, z, what happens? Every vector of V can be written as a linear combination of V1, V2, V3. Hence, these three vectors span the whole space R cube. So, this is how we will do these kind of problems. Span of the vectors, all these three vectors equal to the whole space R cube. Now there is a point to note. If you have three linearly independent vectors of R cube, then those three vectors always span the whole space R cube. The span of those three linearly independent vectors is always equal to the entire space R cube. So that we can have the generalization n linearly independent vectors in Fn always span the entire space Fn. So you can take one example. Take V1 as 1, 1, 1, 1, 2, 3, 2 minus 1, 1. We will check that are they linearly independent or not. I had already made a video on how to check the vectors are linearly independent or not. So you can watch that video. I'll share the link in the description box. So 1, 1, 1, 1, 2, 3, 2 minus 1, 1. Write the given vectors as the rows of the matrix. Find its determinant. We got here non-zero determinant. Therefore, the vectors are linearly independent. Now, as you got the fact that these vectors are linearly independent, you can skip the procedure to check are they spanning the whole space or not. That is because every three vectors, three linearly independent vectors of R cube always span the whole space R cube. You can check with the your method also just to cross check. You will get the same way. That is any vector can be written as a linear combination of these vectors x, y, v1 plus y, v2 plus z, v3. You will get a non-homogeneous system of equations. Solve that non-zero system of equations, non-homogeneous system of equations, and if there exist values for x, y, z, the system is consistent. Hence, the three vectors span the whole space R cube. So this is the procedure to check R whether the given vectors span the whole space or not. I hope you understood the concept. Thank you for watching.